practice final 1 Q2. So first we're going to start with some alpha-beta pruning true-false questions. The first one is that Minimax search with alpha-beta pruning may not find a Minimax optimal strategy. This is false because pruning should not influence the overall result obtained by performing Minimax on a game tree. Pruning should merely eliminate redundant branches that don't influence the final outcome. Secondly, alpha-beta pruning prunes the same number of subtrees independent of the order in which successor states are expanded. This is also false, because depending on the order of successive actions being explored by a Minimax game tree traversal, it is possible to completely render one of the later branches unnecessary, which could actually be explored if the successor states were ordered differently, and this branch was explored prior to other branches that were explored earlier to it. Finally, Minimax search with alpha-beta pruning generally requires more computation time than Minimax without pruning on the same tree. This is also false because performing Minimax search with alpha-beta pruning should ideally decrease the computation time than performing vanilla Minimax search, but in the worst case scenario, the computation time will stay the same. This means that there will never actually be an increase in the computation time if you were to apply alpha-beta pruning on a Minimax tree. Now what we're going to do is that for each of the following Minimax game trees, where the max is at the root, we're going to determine whether either no pruning is done, the maximum amount of pruning is done, or neither, which means that some but not all leaves that could be pruned are pruned. We're going to assume two things. One is that we do a left to right traversal while pruning, and secondly, the leaf utility values are potentially drawn from the distribution of negative infinity, infinity, and not from 0, 1. So before we go ahead and go through our examples, I'm going to clarify a couple of things, especially in terms of the definitions of no pruning, max pruning, or neither, because I know that can be a little bit ambiguous. So if we look at the no pruning tree, or the one on the left, we can see here that we actually can't do any pruning while doing a tree traversal here. And that's because for our node labeled C here, once C sees its left child to be equal to 1, it has two options. One is that if the value of its right child D is greater than 1, then C is going to choose 1 as its value because C wants to minimize. However, if the value of D is going to be less than 1, then C would prefer the value that D takes on, which then influences the value of A in the end, because if you were to evaluate B, B is equal to 0. This could theoretically influence A because C could take on some value. However, we can't prune D's right child either, because if D's right child were to be greater than 0, which is the value of D's left child, then D would choose the value of its right child, which then influences the value of C. Therefore, we can't prune any of the branches here based on the values that are given. However, if we were to change the values of the terminal nodes, like for example in this tree, we changed the value of this child to be equal to 5. In this tree, we can prune D's right child because D sees the value of 5. However, its parent C already saw the value of 1. And since D will take on a value that's going to be greater than or equal to 5 based on its left child, we know that we're not going to choose the value of D as C's value because C would always prefer 1, regardless of what D ends up being. Therefore, in this case, we can prune D's right child. However, we can't prune C's right child, which is equivalent to D, because after C looks at its left child, we know that C is going to be less than or equal to 1. But in this case, we pretty much can see that if C takes on the value of 1, then in that case, A is going to be equal to 1 because its left child B is equal to 0. However, if C takes on some value that's less than 1, so 0 or smaller, then in that case, A is just going to prefer what B takes on, which is equal to 0. So in that case, since A's value is influenced by whatever C ends up being, C needs to examine its right child in order to figure out what its value is going to be. Now if we look at this right tree here that is representing max pruning, we can see here that we can prune C's right child because we changed the value of C's left child to be equal to -1. We saw that C's left child is equal to -1, so the min node C is going to be evaluated to something that is less than or equal to -1. This doesn't influence the value of A because since A is a maxi node, A is always going to pick on the value that B takes on, which is 0, because 0 is greater than -1. So the max node would prefer 0 compared to whatever value C takes on, which could be smaller than -1. So yeah, in this case, we prune C's right child. However, in the context of the problem, make sure to remember that we're referring to maximum pruning as doing the most amount of pruning possible on the tree structure with the given values in the terminal nodes. Therefore, as you can see here for this right sort of tree, we can't really do more pruning on this tree. Since we've already pruned as much as possible, we always need to examine the children of B in order to figure out what B is going to be equal to. And then we also need to look at C's left child in order to establish a bound on what the node C is going to evaluate to in terms of its highest value. And so therefore in this case, since we do end up pruning C's right child, this is the most we can actually prune on this tree structure, and so that would be maximum pruning. Hopefully this is clear. If you have any other questions, definitely feel free to post on Piazza or ask any of the TAs. So yeah, now we'll go into our examples here. We're given this game tree structure, which is a little similar to what I showed earlier, but the structure is a little bit different because now the right child has this extension with a left grandchild. But we can pretty much go ahead and first evaluate what the root node is going to be equal to, and then see, based on that evaluation, what we've pruned and if that's maximum pruning, no pruning, or neither. So we're going to pretty much initialize our alpha beta values to be negative infinity, infinity, and then we're going to pass that on all the way on our left branch of this game tree to the first terminal node that we see here. So that's going to be this node A. We pass on our alpha beta values of negative infinity, infinity. We see that A is equal to 1. So based on that, and since its parent is a min node, we're going to update the value of beta. Because the min node can pretty much take on any value that is going to be negative infinity, 1, because it sees 1 as its left child. So the min node is only going to prefer something, some other value if it's less than 1. So that's what we're going to pass on to this min node's right child. We see that this value of this terminal node here, B, is also equal to 1, so we don't really update anything. And now what we're going to do is evaluate this inverted triangle to see what value it takes on. Since it's a min node and its children are both equal to each other, it doesn't really matter, so we're just going to evaluate it to 1. So now this left child of this root node has been evaluated. We can now update the value of alpha because our parent here is a maxi node. So that maxi node will only take on values between 1 and infinity. So that's what we're going to pass down to this max node's sort of next terminal child, which is all the way down here, this node C. We receive the values, alpha beta values of 1, infinity. Now note that here our sort of parent of this terminal node is also a max node, so we're going to be updating alpha if necessary. However, since we see here that this child here, C, is equal to 0, 0 is less than 1, in this case we just ignore this child because it doesn't really do anything in terms of the values that influence our sort of game tree structure here. So we're just going to take this alpha beta value pair and pass it down to our next child, which is also equal to 0. And so we don't do any more update of alpha beta here. So then we can just evaluate the value of this max node here, down here. It's going to be equal to 0. Now, since we've evaluated this child of this min node here to be equal to 0, we can update the value of beta. And since we update the value of beta, which is currently infinity, to be equal to 0, this is the best value for this min node so far. And since we see that 0 is less than 1, which is the best value for this max node up here, this max node will always prefer 1 over whatever this min node evaluates to, which is going to be 0 or smaller. And so since we found that out, we can pretty much stop our evaluation of this min node and the rest of its children. So we're just going to perform pruning on this branch here that contains this child E. So yay, we do pruning. We don't have to explore anymore. We can just take that out. We can evaluate this min node to be equal to 0 because it's just going to be 0 or something smaller, and that doesn't influence the value of the root. So our root value here is 1. In this case, we've done maximum pruning just because if we were to change any of the values in this tree, we wouldn't be able to prune any of the other branches. And this is because we need to know what the value of all A, B, C, D are, because this could potentially influence the value of the root. And we don't know if it would or would not because of the updates to alpha and beta that are happening within this tree traversal. So yeah, we're doing maximum pruning here. So now we'll move on to our second example, which has a slightly modified tree structure, but still somewhat similar values of 0 and 1. So we'll perform a tree traversal here as well, where we initialize our alpha beta to be negative infinity, comma infinity. We pass that down all the way to our first terminal node here. That contains a value of 0. Now, since its parent is a min node, we're going to update the value of beta because our beta or our min node here can take on values between negative infinity and 0. So that's what we're going to pass down to this min node's right child. We pretty much see that the value of the terminal node B is equal to 1. And since 1 is greater than 0, which is the min node's best option right now, we should not be updating our beta value because the min node has a better option. So we're just going to select 0 as the min node's sort of value because that's its best child out of A and B in terms of the values. So once we've found this value of the root node's first child, we can update the value of alpha because it's a max node. So we're going to pass down the alpha beta pair of 0, comma infinity all the way to the next terminal node, which is C. We see that the value of C is equal to 1. And since its parent is a min node, we're going to update beta and then pass down that alpha beta pair of 0, comma 1 down to the next child, which is D. We pass down 0, comma 1 to D. We look at D's value, which is 0, and since its parent is a max node, we would be updating alpha here. But since alpha is already equal to 0, we don't really need to update anything. But in this case, since we haven't had any violations in our ordering of alpha and beta, the potential, child E could potentially have an influence on the main value of the root. And so that's why we can't prune E, because it could theoretically have an influence depending on what value it takes on. I would recommend maybe looking at the example that we went through earlier with the 3 different trees and seeing how changing the values could potentially cause it to be pruned. But in this case, since we have no violations of our alpha and beta, we can't prune it, and so we evaluate it. We see that it's also 0. We don't make any updates to our alpha beta pairing, and then we can just calculate the value of this max node by taking the max of its 2 children, which is going to be equal to 0. That means we've evaluated the right child of this min node here. We can pretty much take the min, which is also equal to 0. And then finally, that means we've evaluated the children of this root max node here. So we can just take the max of both of its children, which is going to be equal to 0. So since we haven't pruned any branches here, we're just going to select no pruning because we needed to evaluate all children in order to get the final value of this tree. And that's it.